let's take regeneration. This is the idea where you're building an amplifier, but it's a power amplifier, but instead of being a power amplifier for audio frequencies, it's a power amplifier for one frequency, 60 hertz in North America, 120 volts out. So if you need a voltage regulator, that's as good as it's ever going to get. But the thing is that most of our equipment does not. It's got direct current DC regulation inside its power supplies for most of the critical circuits. So that's usually redundant to begin with. And it's also fabulous for getting rid of any level of harmonic distortion. There are times that that's incredibly useful, but for the most part, it's not, because any component other than an AC synchronous motor and a turntable without a outboard power supply, that's the one exception. But for everything else, it's about to go into a power supply through the AC cord that's going to turn alternating current into DC current. Once it does that, your 2 to 4%, sometimes double-digit harmonic distortion goes down to 0. So it's a direct current at that point, similar to a battery. So that's not necessarily helping you too much. Is it better than the wall? In many cases, yes, it would be. In some, maybe not. Because here's that thing that you were talking about right at the beginning. You got to look at the application. First of all, are you going into a power amplifier? Well, if you are, power amplifiers have something that's very unique amongst anything else in an audio video system, and that's that it's the only component where the power supply is not drawing a constant current. It's drawing a variable current. And that's a problem, because even fairly modest power amplifiers, integrateds and receivers, can end up drawing very, very briefly, 10 to 15 milliseconds, a blink of an eye, a transient current draw from your wall that could be anywhere from 30 amps up to 80 amps peak. Just, like again, for just a very brief period. So the problem when you go through a power amplifier feeding a power amplifier is that it behaves like an amplifier. What do all amplifiers do when you push them too hard? They clip, they distort. Everyone knows this. All of a sudden, that perfect sine wave that regulator can, or that regenerator can create under ideal conditions, say it's a 10 amp, like a regenerator, okay, the sine wave looks virtually textbook, beautiful. Right out of engineering school, that's what I would have gone to. But what I know better now, because we made things like this when I was at Furman, is that as soon as you hit 1.414 times the fundamental, approximately 41% greater than that, about 14 amps, it's going to start clipping. At 20 amps, that sine wave doesn't look good at all. By 30 amps, your wall looks better. It's current compressing. Strike one. The second issue is that what do all amplifiers have in common? They have a frequency response. They're all going to be different, but that's its bandwidth. Let's be generous and say a power amplifier has a bandwidth of 1 hertz or 0 hertz up to, let's say 500 kilohertz. That would be pretty wide by most standards. I've seen a few things that go up to a megahertz, but it's rare. Okay. What happens, just like an active RAAA stage in a phono preamplifier, what happens when you run out of frequency response or bandwidth? Your filtering's gone. You've just gone from over 100 dB of noise reduction, boom, to 0. You're going to have ringing properties that you're going to be, because that's nonlinear, uneven. You're going to have ringing properties that you're going to hear for 5 octaves below that. And right at the frequencies where induced radio frequency noise are the worst is where that idea stops working. It's not that there isn't noise below that, there is. And that technology will do a splendid job of dealing with those noises. But the thing is, there's over 23 octaves of noise that exists on an AC line and also bombard it, as an antenna from radio frequencies. I don't want to say that I know the magical frequencies that matter. There is no such thing. These all turn into noise that masks a little detail. I want to get them all. Can I get them all? you know, if I can't, I want to get as close as I can to it. And I'm willing to have lower noise reduction or dissipation numbers if I can get that noise dissipation or reduction to be as even or linear as possible. That's critical because I don't want at one set of audio frequencies a result where my low-level detail is unveiled and unmasked almost perfectly at 1 octave from here to here, only for a quarter octave away, I'm only 10 dB down, and I've gone from here to here, and then I've got a noise peak that my technology has created under real world, in what are called impedance conditions, and I'm actually adding 6 dB of noise. And for, you know, like for all the octaves of audio, I'm literally going from here to here. It's discordant. It sounds wrong. It's, once again, back to what you said before, Adrian. It's the idea that, well, I like some things about this, but I like, there's other things I'm not real sure about. I need a consistent result every time. And to do that, I've got to understand what my real world load impedances are going to be. And we got to deal with this. You can't deal with this effectively with something like regeneration. It'll have some good points, but it's going to have some whopper and some doozies of negatives. And, you know, like